Okay, I'm recording now. Um, well, the work for next week and the third session is still part of Module 2, but it's kind of a different block. In Module 2, the first part of Module 2, which is today and the work you did this week, we're working at a high level. We're working with the peripherals, but at a high level, meaning that we're communicating from our programs with the peripherals through the memory mapped registers that are defined in the SOC. In the second block, it's in the GitHub, it's called Module 2B. In the second block, we're going to work at a low level, meaning that we're going to work with a very low code that is available because this is an open source and we can access and see and analyze and change the controllers that control the different peripherals. We can add new ones, we can do whatever we want, and we're going to work at that level. And the objective is to understand how one of these peripherals, the 7-segment displays, is controlled. Let me see, there is something here. Okay, someone has to admit. I was saying that we're going to, the objective is first to understand how the 7-segment displays are controlled in hardware, and I will talk a bit about that now, and then to extend that controller in order to provide different functionality to the 7-segment displays. Note that for that, you will need to regenerate the bit stream. You won't use the original bit stream in these exercises, but generate a new one with a new functionality and then play with it in a program. Okay. This is the GitHub. This is the summary of the tasks to complete next day. And if you go into Module 2B, you can find more details about this. So let me show this. This is Module 2, second part, low-level input-output. And this is the description of the previous work to complete before next session, third session on May 29th. So first of all, you should understand how the operation of the 7-segment displays Verilog controller, which is implemented inside this file. This is the whole path to the program, to the Verilog module, which is called Swirlwolf Syscon. Syscon is for system controller. This controls different parts of the core, and among them, it controls the 7-segment displays. The other parts are not necessary for us now. We'll focus on the 7-segment displays controller, which is included in this module. If you open that module, I have it here. You can open it in your virtual machine, in the sources for the SOC, and you will see this. Let me say that all this is described in high detail in the video that was recommended before today's session. Okay, part of it, if you've seen the video, part of it you've seen that it's talking about the low-level details of the Verilog module implementing the 7-segment displays controller. So please look at that part of the video again in order to help you understand the controller. I'll go with that program in a minute. Let me first read this part. So in addition to the path to the module, we also recommend you to use a simulation in RVFPGA trace. Remember the simulator when you were familiarizing with the different tools that we have in RVFPGA. One of them was the RVFPGA trace simulator, which lets you generate a trace for a program and analyze the different signals. This is a figure of an example trace that you use here, and you can analyze on the left. You can see different signals of the SOC that you can watch in time, as how they change in time. Okay, this is time. You see here picoseconds, and you see here the signals that we've selected for showing in the simulation. You can add any other signals inside the core or the shock that you want to analyze. This is just an example, but you can add any other signals. This is generated with Verilator, which is a simulator of Verilog code. Probably you're familiar with it or you've used it. And this is visualized with GTK Wave, which is an application that lets us visualize these kind of traces. So you can download this project, which contains the example that you can work with in order to better understand the program, because it's maybe not so easy to just read the Verilog code, and it's much better to use, in addition to reading the Verilog code, use a simulation that lets you see in time any of these signals. Okay, so that's our recommendation, that you understand the controller by reading the code, analyzing it, but also running a simulation in RVFPGA trace that lets you analyze single or individual signals a long time. Okay, let me go inside the code. This is, as I said, this is explained in the video, but let me do a summary here. So in the module, if we go to the beginning, you will see this is the module name, Swirl Syscon for system controller, and it has several signals that we don't need to understand for our objective, which is the 7-segment display controller. So let me skip this initial part and go to this part. In this part, in this case statement of Verilog, I don't know if you know it. If you don't, please review these concepts in Verilog. This case is selecting the different the addresses received from the core. So when the core generates an address, it loads or stores data from an address. This will come here, and this is like a multiplexer that will forward the address and the data from the core to the different peripherals. And specifically, we're not interested in all of them, but only in this final part here, 14 and 15, which are the registers related with the 7-segment displays. If you look at the name, it's enables reg and digits reg. If you remember, when we talked about the 7-segment displays controller, we said that it receives two signals, enables regs and digits reg. Let me open again the slides that I showed before, presentation lab 4, and let me go to the slide showing the picture for the 7-segment displays controller. Again, this is explained in the video, so you can find it there if you want. So this is the system controller, which is included in the SOC, in the FPGA, and these are the two register, enables register and digits register, that are inputs to the 7-segment displays controller, and which are set, which are written from the core, from the EH1 core. Okay. So you can see those registers here in the code, in the Verilog code. These are these get as the data from the core. This is something, this IWB that comes from the core, and this is written to the register that will write something to the 7-segment display. So you can see the low-level process here in this part. Now, if we advance in the file and go to the end, you can find what is more important for us in this module, which is the 7-segment displays controller implementation. Sorry, well, this is the instantiation of the core, this part. This is instantiating this module, which is programmed below here. This is the implementation of the 7-segment displays controller, which has several lines, as you can see, and which you should understand. So this is the first task for you to do before next session. Understand how this module is programmed. And as I said, you can both read the code, try to understand it, and also run a simulation in RVFPGA trace that allows you to show all these signals, internal signals, and how they evolve in time. Okay? Specifically, as you can see in the provided project and in this simulation, you can see 4 of them, 4 signals. Look, this is the interface for the module. In addition to the clock and the reset, you have the enables register that comes from the core, the digits register, which also comes from the core, and which are shown in the simulation, enables reg and digits reg. And these are the input signals to the controller. And these 2 are output signals from the controller. And these will go directly to the 7-segment displays peripheral. These are the signals that will control what is written to the peripheral. And they are called AN and digit bits. And you can see them here. So the first 2 signals, enables reg and digits reg, are the input to the controller. The two last signals are the output to the controller. And if we go back to the presentation, these are the signals shown here. Enables reg and digits reg are inputs to the controller and come from the core. And well, they are renamed here, but they are the same as these 2 signals, AN and digits bits. Digits bits is renamed to CACD. These are 1-bit signals, but they are exactly the same as this array of signals that we see here, digits bits. And AN is this AN0, AN1, and so forth. So these are the 2 inputs to the controller. These are the 2 outputs to the controller. The controller must understand how the physical peripheral works in order to transform this information given by the core in the enables register to the signals, to the physical signals that the peripheral needs. And this requires the controller to understand how to communicate with the peripheral and how this is connected physically on the board. This all is described in the video. So please look at the video carefully, repeat it several times if you need to, until you understand how the physical connection of the peripheral is done and how the controller is programmed in Verilog in order to transform the information from the registers into the signals needed by the peripheral. Okay, this is the first task that you must do for next day, which is the main task, in fact, is the part that you have to dedicate more time to, as it's the most difficult part. Let me know if there are any questions. Probably you haven't looked at the Verilog code yet in detail. Maybe if you have seen the video, you've gone through that part and you've probably understood it, at least in part. But you have to look at the video and carefully look at the program in detail and maybe several times for understanding it correctly. Okay, but anyway, do you have any questions already? Okay. Next week, while you're analyzing the Verilog program, if you have questions and you have there are things that you cannot understand, specific things, you can write me an email, you can ask for a tutorship during the week, no problem with that, okay? Okay, second part of work to do before next session, this is much easier, is to install Vivado in your computer. Why is that? Well, we will, as the exercises for next session, we will extend the controller. Once you have understood how it works, we'll ask you in the first exercise to modify it. We'll ask you to extend the functionality of the controller in order to do a different thing. Everything is described in the exercise, so you can read at it, but it's part of the third session. So we'll look at this exercise next day. For now, it's the first task. You understand the controller so that you'll be able to modify it. And once you have modified the controller, you will have to regenerate the bit stream. And that requires you to use Vivado. Vivado is the silence tool. You probably are familiar with it. It's the silence tool that lets us synthesize hardware for an FPGA. We want to resynthesize the whole SOC in order to support the new functionality for the 7-second displays. Okay, so first, before next session, you have to install Vivado. Vivado is available for Windows and Linux, not available for Macs, for Mac computers, at least as far as I know. So these are the instructions for you to install in Windows. These are instructions you can find in the internet, in the Vivado installation web page. Vivado is free, at least the Webpack edition. There's a small version that you can install for free, so that's good, and that's enough for us for what we want to do. There are licenses that you have to pay in case you want more functionalities, but the free version is enough for us. So you have to select that version. These are the instructions for doing that. Summarize the instructions. Maybe you have to look at more extensive instructions in the internet in order to install it, or maybe this is enough for you, whatever. Please follow these instructions to install Vivado in a Windows machine or a Linux machine. These are for Windows. Linux instructions can be found on the web. These are links for the Vivado download website. And this is for a link for adding specific boards that you will need to follow. The reason is that the default port supported in the Vivado version that you'll install do not include the Nexus 87 board. So you have to install support for that board after you have installed Vivado, and you can follow the instructions provided here. Okay, Vivado is quite big. You will need some spare space in your disk to be able to use it. In case, given that many of you are working together in the same company, you probably can share it. If somebody cannot use it in his or her own laptop, maybe you can share one of somebody else or something like that. Well, you can manage it. Those of you who are working on your own, don't have colleagues in the course, will have to install it yourselves, or you can come to the lab and use it here. Okay. Any questions about the two tasks that you have to do for next day? Again, if you have any problem, any question with Vivado, ask me. Yes, Joseph.
Yeah. So we have to install Vivado for. Can you hear me?
Can you repeat?
Yes. Okay. Yeah, so we have to install Vivado for next week, but can we do everything on the virtual FPGA still? Or do we need the actual board for the next session?
You need the board. Well, let me see. You can open simulation. Why is the question? You don't have the board.
No, I have it, but we cannot connect it through the Windows subsystem for Linux.
Okay.
So maybe for next week we'll not have it available.
The instructions in the module tell you that you can use or explain you how to use the board and the simulation. You can do the activity in the RVFPGA Bitbo simulator. Okay, remember from the tools, there is one simulator that uses a virtual board, and you can do the same exercise on the simulator. From my point of view, it's better if you can use the board, but if you cannot, at least you can use the simulator. The instructions are given in the same task here in the GitHub. You can see that everything is explained for the FPGA board and also for Bitbo. Different instructions, but same functionality, exactly the same. The same program that you develop or the same changes that you do in Verilog should work in both tools. Yeah.
Okay, good. Thanks.
More questions? Okay, let me stop recording from my side. This is it. No more explanations for today. I will share this video through the GitHub in case you want to review it or somebody has not been able to attend today's session. And well, from now until 2, you can continue working on the exercises for today's session. I will stay here. If you need to disconnect or leave now, you can do that, no problem. Work on your own. Ask me any questions that you have now until 2, or through email or through a tutorship. Okay? Okay. So thank you.